Hi, my name is Manan Suri, and I'm going to talk about AgentLens, which is a platform that we built to analyze and visualize agent workflows. LLM based agents leverage large language models to understand, generate, and interact with human language, enabling complex tasks like problem solving, dialogue, and decision making. These agents harness the power of pre trained models, applying them to diverse domains such as customer service, data analysis, and content generation. Their ability to adapt to various contexts, along with their ability to access reliable tools, makes them versatile in various applications. We built this platform mainly for agent developers and people who are building these agents using LLMs to analyze things such as latency, errors, and performance. The first view that we've got here is the tools view. You can see different tools that we have and basic metrics about each tool, such as what's the average time taken, the error rate, the average number of tokens that the LLM spends in prompting and completing for this specific tool. And we've also visualized the distribution of durations, so fast, average, slow, and maximum. We also look at the stepwise distributions because we've got a tool calling agents, which looks specifically at tools which are operated in discrete steps. So, this tool, for example, as you can see, is mostly used around the second or the third step of the simulation, whereas this tool is predominantly used early on in, let's say, the first and the second steps of the simulation. uh, we can change this view to sort these tools by various metrics. So let's say if I want to find what tool creates the most number of errors, I could sort it in descending order by the error rate, which gives me the tool called OutDegree, which has an error rate of 42.9%. Now, as a developer, I might want to interact with this visualization to find out what's wrong. So I can click on details to look at detailed and to look at a detailed analysis of what happens with this tool. So the pie chart representing the token distribution shows us that completion tokens are typically much less than the prompt tokens, which is typical for all the tools in our data set. Uh, we see that in terms of runtime distribution, uh, on average, failure or error cases take more time to run than successful cases, which could also contribute to higher latency because this tool is failing repeatedly. We also find that uh, we can also look at the joint distribution of the duration, that is the time taken to execute this tool, versus the number of tokens that are exhausted in this. And ideally, you would want to analyze use cases where there's a high usage of tokens, which translates to monetary costs, and a higher duration, which could be critical for certain applications. We can also look at historical performances by looking at like the performance of this tool across like various uh, runs that have been performed with it. uh, Step analysis tells us the distribution of time taken per token by step. This is just a metric to measure both of these things simultaneously. The error rate by step, and we can also look at the average duration by step. Further, the execution timeline shows different execution IDs and uh, dif- the location of like errors, the number of prompts used, and the duration. We can also look at the step distribution timeline. So, depending on like different execution IDs, we can see that in a lot of them it occurs in the second step or less than the second step, and only once it occurs at the fifth step. This is about the tools view. We also have another view called the overall metrics. The overall metrics is used to visualize the system as a whole. The first thing that you can do here is select which tools you want to visualize. So we've already pre-selected the top 5 tools in our system, and let's say I also want to look at OutDegree, I could add that. If I want to remove certain tools, like final answer, I could do that as well. Uh, this is a basic summary of uh, the aggregates of all of these tools together. So the average duration, the total number of tool calls, error rate, and average tokens. Uh, since our system operates in terms of steps, we can also plot the error count by step. So this tells us that for some reason the tool, which is the BFS tool, spikes at step 2, like it has a higher number of errors at this step than other steps, whereas get descendants usually fails early on in the simulation. We also have an overall visualization of the success versus error rate for this subset of tools that we are seeing. We can look at the duration versus token count for all of the tools that are plotted, the token distribution by tool, which is a stacked bar chart, but since the number of tokens for completion are less, uh, this is more or less similar for all tools. What This is important to plot because there could be tools which are utilizing too much completion tokens or prompt tokens, and even minor differences over time can lead to huge monetary costs for the developer. Uh, we can also look at the distribution of tool calls by specific steps. So amongst the tools that we have selected, we can see that in the first step, it's get descendants is the most common tools amongst all of these, whereas step 2 has a higher like tool usage count amongst the tools that we are using. We can look at the trend analysis by step in terms of the average duration and the average tokens. The average tokens remains more or less consistent, whereas the average duration is high for step 1, meaning that the system needs to optimize uh, like code compilation, which happens in the first step itself. We can also look at runtime distribution for these tools, these selected tools, by as a box plot, and this is an interactive box plot. So let's say if I want to reduce the outliers, I could plot it only till like 10 seconds perhaps and look at the distribution better. We're plotting success and error runtime distribution plots because both of these could be helpful in analysis. Finally, in the overall metrics tab, we've got a duration heat map. Uh, this basically analyzes the tools that we have and the time that they take in each time step. So it looks like out degree is a tool that takes a lot of time in the first step itself, uh, meaning we could somehow optimize this, reduce its time complexity, and get descendant stands out in step 4 because on average it ends up taking 4.2 seconds compared to other uh, tools at this specific time step. Finally, we've got another view, which is the tool flow uh, view. So this is a Sankey chart which shows the transitions of the tools across agentic steps. So when you look at the normal view, you can basically analyze what sequences of tools exist. So it looks like a very common sequence is a triple of get statement tool calls across the system. Uh, you can hover over the nodes or the links to find out the counts or the different details regarding this, making it accessible. Uh, we Since final answer is a completion node, this can also be used to point out that uh, most cases, like step 3 is a case where majority of the uh, majority of the simulations end with the final answer. We've also got an error view to the tool flow Sankey to analyze how errors propagate in terms of transitions between agentic steps. As you can see, it looks like get neighbors generates a lot of errors in the first step itself, and uh, very often it tries to rerun the same function, that is get neighbors, after it has an error again. This could mean that perhaps like initial function calls were incorrect, and the success rate increasing after that would mean that this system is able to self-correct and run this function correctly later on. Uh, we and there are many such interesting patterns that you could find over there, but we also summarize error statistics at the end of this by like plot writing down the error overall error rate as well as the error rate by tool. That's it. Thank you.